everybody's packet should have an exorbitant amount of question marks at the end because I fixed a typo during Panther period and then reprinted. So yeah, all right, I think we're good. I didn't hand out the wrong packets. Cool. All right. So we're going to kind of do we're going to look at kind of two things today. The first part is, what is calculus? That's probably a good question. We know what algebra is. That's x's and y's. We know what geometry is. That's shapes, duh. Who knows what trig is? I don't know. But what is calculus? That's our focus. Basically, calculus is the part of mathematics that focuses on the study of rates of change. If you have ever solved a problem using a rate, which you have, then you have solved the calculus problem. There are, especially in what we're going to study, there's kind of like two branches of calculus. And these two problems in example one are calculus problems. They're very easy calculus problems. You don't need calculus to solve them. But you should take a second, read those two problems. Feel free to use any calculator that you have handy and come up with some answers. Let's see. All right. All right, so question on the left, how fast is our object traveling? Yep, 1.5 meters per second. You got that. Easy. Algebra 1, middle school. Both places we've learned stuff like that. And number 2, how many people could go on the escalator in an hour? 13,500, sure. And we did that. Actually wanted to write the math to it. So we had 90 divided by 60 to get that. And we did 225 times 60 to get 13,500. Cool. So either we're done, because that's it, that's all there is to calculus, or there's a little bit more to the story. Idea here is both of those problems involved a constant rate of change. On the left, it explicitly said it was a constant rate. Because we were looking on the right for like a maximum, we were saying like, what if we, filled there was a big line in front of the escalator and we really put it to its max, that ends up making that rate constant, 225 per minute. So both of those were somehow baked in a constant rate of change. What's going to happen in calculus? We're going to make that rate of change not constant anymore. So before we actually do that, I want to take a look at example 2 because this is a good preview of what's to come. There are a lot of different questions that I'll ask you to do the same thing in calculus. So that's one of the things about calculus. There may be 3 different ways for me to ask you to do the exact same question, and that's part of it, is identifying, whoa, okay, they asked me this, so now what process that I learned do I have to do? So on the left, I have a graph. It sure represents that same information from the problem above, right? It goes to 60 seconds, and the distance traveled is 90 meters, but the question's different. It's saying, what is the slope of the line graphed above? Well, what is that slope? Grab some points. Yeah, it is up 3 over 2. So it's 3 halves, which sure is 1.5, right? somewhere along the line here, I have to use 2 fingers to scroll. I'm not sure why, but anyway, yeah. So same question, same information, different question, but really the same question, same answer, same thing. All right. And then on the right-hand side, same information. People are getting on the escalator at a constant rate of 225 people per minute. What is the area? A little bit of a weirder question. What's the area of the rectangle bounded by the x-axis, that line that's graphed, and in between 0 and 60? Now, I'm not asking you to find the area by counting up those little squares. I want you to use the numbers. So this doesn't represent a, like, I don't know, looks like maybe it's like 1, 2, 3, 4. I don't know. It's like 10 or 15 going up. But I actually want you to think of a 225 by 60 rectangle. That's the same problem, right? I just have to multiply those 2 numbers. It's not a hard problem. It just kind of jumps out to the fact that this is what happens to us a lot in calculus. Same question, same information, different question, but really the same question. All right. Got a big eraser. Okay. So now here's what I want you guys to do. Take a look at these follow-up questions. If you're sitting next to somebody, you can do this in partners, maybe divide and conquer, one do the left, one do the right. Those are just demarking whether I'm answering the question for the left or the right. I don't know why I chose to use that, but that's what I did in period 1. There's kind of 2 questions, or there's a question here for each graph. How does each graph show a constant rate of change? Left graph, right graph. How would each graph look different if the rate of change was not constant? And how does that make the problem harder? Why do we have to spend a whole year learning this stuff? Yeah. All right. So starting with the graph on the left, how do we know that that's a constant rate of change? Go ahead. It's a line. Yeah, it's absolutely. It's a line. It's a linear equation. It's a line. Both of those work. That is the defining feature of a line. No matter which 2 points you pick on it, you always end up with the same slope once you divide, simplify, whatever it is that you do. So yeah, definitely it's a line on the left-hand side. It is also a line on the right-hand side. On that graph, would any old line represent a constant rate of change? This is the nuanced question that I think is easy to miss. If I drew a diagonal line here, so different function, different line, different whatever, does that represent a constant rate of change on that graph? See some no's. Why not? What's different about that graph? Good. Yeah. Escalator. What is this thing? This escalator you speak of? think you're close. Do you want to say something, AJ? No. What's different about that graph? It's like, this really speaks to something that can really throw us off down the road, which is why I always like to bring this up on the first day. What is different about that graph? Why is that diagonal line? Two different questions. Why does that diagonal line not represent a constant rate? That's it. Absolutely. Yeah. So in a way, if you really want to get deep into it, you're right. It does represent a constant rate, but it's the constant rate of people per minute. But if we're thinking in terms of simplicity, this is a graph of a rate. So the only way for that rate to be constant is if that line doesn't go up or down. So for what I'm trying to say, that's definitely the direction I want to go on it. So for this graph, in order for it to be a constant rate in terms of people per minute, then we are talking about, we need to actually have a flat line or a line with no slope, or line with zero slope. But the reason for the difference there is because of the way that the graphs are laid out. But again, this speaks to the two main things that we'll be talking about throughout the year. So I think that kind of makes these next questions a little bit easier. So how would they look like if the rate of change wasn't constant? And what would that look like? A curve, yeah, absolutely. So yeah, so on the left, you would need a curve, right? I hate when I do that. There we go. Yep, go away, curve. And on the right, obviously a curve would work too. I mean, but you can even have a diagonal line, just to kind of point that out. And these aren't all inclusive, and I'm not saying that you couldn't probably make an argument for something even more complicated than this, jumps in your graph and things like that, but these are just kind of the ideas. So now when you think about a graph that has those instead on, let me stick a curve on this, then you lose what I said earlier, which was the defining feature of a line is no matter which 2 points you pick, you're going to get the same result when you figure out the slope. If you pick 2 points on a curve and do rise over run, and then pick another 2 points on a curve, you're going to get a different result no matter which 2 points you pick. And that's something we're going to look at a little bit deeper into this lesson. So yeah, so you don't get, so that makes this problem more difficult because you're not getting consistent, you're not getting the same result everywhere. One way to say it. Totally different than what I wrote in period 1. You know, these are just kind of loosey, open-ended sort of questions. And then think along those exact same, excuse me, along those exact same lines on the second graph. If I drop a curve on here, if that's my rate for whatever reason, think back to geometry. More people than not had Stallnecker. Did Stallnecker teach you how to find the area of that shape? No. If you didn't have Stallnecker, did your geometry teach you how? The answer should still be the same. But yeah, so that's kind of the main two things that base everything we do throughout the year. Kind of these two issues that we have. Finding a slope when we have something that isn't consistent, and finding an area of some sort of shape that isn't just a regular geometric shape. We don't have an area formula, so that's what we have here. Again, these are very open-ended, and I don't remember what I had in period 1, but it was neither of those two things. But it was the same idea. All right. So I think I've pretty much said everything in that top paragraph there already. Words just keep me on track. But again, we're looking at these two problems. That's what we're going to spend the bulk of our year until the last unit. Really, it fits in one of those two neat categories. Whether it's the graph or whether it's the word problem, they're all the same problems. They just sound different. Okay, so here's the part where I get to the typo that I changed. So hopefully I fixed everything. Let's take a look. So we're kind of moving into, well, then how do we figure out? Sorry, let me try to say this right. How do we start figuring these things out when they're constantly changing? Basically, what we're saying is if something's moving 90 meters in 60 seconds, it may be at a different speed every second. It may be at a different speed velocity every 10th of a second, every 100th of a second. So how the heck do we figure that out? How do we measure that? I'll start off by saying even if we're not moving at a constant velocity, that 1.5 meters per second still has a meaning. If something moves 90 meters in 60 seconds, that is its average velocity. It wasn't always traveling 1.5 meters per second, but if you had one object that was changing but had an average velocity of 1.5 meters per second, it would get to the same place in those 60 seconds as the object that was changing. That's what an average velocity is. So it tells you, what is it moving like? If it were going at a constant speed, how fast would it have to go to get to the same place? And we can use average velocities to help us estimate instantaneous velocities. Now, when we're doing that, our basic question in example 3 is basically saying, now we have an object that is not moving at a constant speed, constant velocity, but we do want to estimate how fast it's going right in the middle at time t equals 30. We have some information. Decided to give you a table because we haven't looked at any of those yet. These are the common thing to see in calc, looking at data in tables like this. We want to estimate how fast that object was going at t equals 30 seconds. We could use its average velocity and say, hey, I think it's going 1.5 meters per second. But that's probably not the best estimate that we can make. A better estimate would be using the numbers close to 30 seconds. If I figure out the average velocity between 29.9 seconds and 30 seconds, that probably should be a good estimate for how fast that object was going at 30 seconds. The question asks to make 3 different estimates because nothing's saying I have to start before 30. We'll make one after 30, and we'll even make one that goes all the way around 30. So we can do a bunch of average velocities and use them as an estimate for that exact rate of change at an exact time. But again, they are just estimates. So if I wanted to use 29.9 and 30, I would do the same thing I was doing when I was doing the slope. I just want to figure out how much the distance has changed and how much the time has changed and divide them to get meters per second. So in this case, I will correctly do 45 minus 44.9 to find out that it traveled 0.1 meters. And how long did it take it to go those 0.1 meters? 30 minus 29.9, which also happens to be 0.1 seconds. So for one estimate, we would say that our object is traveling 1 meter per second. Yep. Okay. Figure out the other two. Use different color here. I had to re-image this tablet, so my colors aren't the way I want them. All right. Do one with 30 and 31.1, and then do one, this is going to be fat, with go around 30, so skip over 30. They'll all be average velocities in time periods that are close to 30 seconds. And they'll come out nice and neat, I think. So with my slight changes and my apologies for the unfixed typo, we come up with 3, again, kind of a constructed example here, but we kind of come up with 3 different estimates for how fast this thing was moving at 30 seconds. 1 meter per second, 3 meter per second, 2 meter per second, right? Okay, cool. So again, idea for this is to just give you a little bit of a flavor of what we're kind of doing here. But again, we have 3 different answers. So who's to say one's better than the other? You could split the difference with the 2 meters per second, but that's just an educated guess at best. Before we jump in and actually see an example of how we can do this or where we're going, a little bit of vocab here. We were given a table, but we're doing the same math that we're doing when we're finding a slope, right? We're taking a change in y, a y2 minus a y1, and dividing it over a change in x, an x2 minus an x1. We are finding the slope of a line in each situation, and that line has a name. It's called a secant line. So if you've identified 2 points and you have a line that passes through those 2 points, that point is a secant line. And when you find the slope of it, like we were doing here, you are estimating what the rate is somewhere between those 2 points. Secant line, similar definition to what you learned in geometry, but they were very specific to circles. They had to hit twice. I did find this example where it hits a third time. We're just not concerned with that, so that doesn't matter. The math that we are doing to find the slope of that line has a name that we use, and we call it a difference quotient. We took the difference, we subtracted, and then we divided. So it's a functional definition. It tells you what you're doing. These things have a meaning. It's very common for scoring guides on the AP test to actually want to see this work. So it's probably one of the most common things, especially at the very beginning of the class, that we'll be, always writing out. So get in the habit of always showing that work. And we just refer to this as a difference quotient. So we have a name for it. All right. Okay, so let's see a little bit of this in action, and we'll kind of get to our definition of a tangent line before it is time to go. All right. We need 2 points to do a difference quotient. That's really the key. We can use, in that last example, we could use t equals 30 as one of those points, but then we need to pick a different point to use for the other one of those points. So let's kind of look at this as an example with a function. I'm going to pop up Desmos, and we're going to kind of just go through this table. You guys will fill in, this screen will be gone. You can kind of fill in it as I go along. So we have a function. We've got a little bit more generic here. F of x is 5/8 x minus x squared over 4. And we are honed in on the point x equals 2, which is the point 2, 2. That we'll see on our graph. That's really what we're thinking about. We want to know what the rate is that this function changes when x equals 2. And we're going to fill in this table to sort of see if we can figure that out. So let's take a look. So it gives you a little bit of a visual here. We'll do this later on when we're doing this a little bit more formally. You guys will do this on Desmos yourself, things like that. Desmos is actually the calculator that you guys have access to when you take the AP test. Only on 1/3 of the questions, but when you do have a calculator, in addition to your graphing calculator, you have basically what we're looking at on our screen here. I've pre-populated a lot of it, though. I have our function. For some reason, it's reversed from the way it is on your paper, but it is. The first thing that we want to do here is find the slope of a secant line that goes from x equals 1 to x equals 2, and I have Desmos set up to do that for us right here. It is taking the f of 1 minus the f of 2, and then doing 1 minus 2 down there. So it is calculating the difference quotient for us for free here. So in that first spot in your table where a equals 1, put in 0.875. That is an estimate for the rate of change at x equals 2. And then I think the next number that I have is 1.5, so I will change that. I'm going to bring that point a little bit closer, and I think I'm going to get a better estimate by doing that. And now I've reduced my number to 0.8125. Man, it's a calculator, and it does the math for me for free. I can get even closer. I can hit 1.9. And you can see those points have gotten really close together. And I'm at 0.7625. I want to get closer. I want to get closer. I can keep getting closer, but the thing I can't do, oops, sorry, I can't get closer. I jumped ahead of myself in my narration there. 1.99. Man, I can't even tell that those points are different unless I stick my head really close to the board. But now I'm at 0.75125. But again, I just have an estimate. I have the average rate of change from time equals 1.99 to time 2. I can't get to the point. I can get close, but I can't get there because as soon as I put 2 in, what's my difference quotient? Undefined, right? Because I have math that wants me to do 2 minus 2 in the bottom. I can't do that. But I don't have a line. I want to have a line there. The reason I want to have a line there is watch what's happening. Everybody's got, yeah, you just had it right undefined there. I gotta go off it and then back on it, I think. There we go. Let's get my slider back. Like we have this nice, what's gonna happen is we have this nice line that just moves smoothly as we move our point, but disappears when we hit 2 and reappears. And our goal is to find out what that is. So we'll keep going. We'll fill in the other side of the table, and then we will make our estimate. So we need 2.01. We have values again. That's 0.74875. 2.1, 0.7375. And then we'll go some further away estimates. 0.55, 0.5 is not a number. 2.5. And then we'll finish off with 3, 0.625. All right, so I'm going to flip back here for a second to my, now you guys have all those numbers filled in your table there. 2 was undefined. Can you guys remind me what was in 1.99? Cool. And what was in 2.01? Yep. And of course, knowing that I've taken a nice example that's going to come out nice and evenly, what number do we think we want to put there where the 2 goes, even though it's undefined? What seems like a nice, good middle ground between those 2 numbers? It's all good. What's a good middle ground? What would we want to define? What number would we want to have here so that line moves smoothly? 0.75, right, yeah. So based on the numbers from that table, we think a good estimate for what that number should be there where the undefined is 0.75. And now the biggest ultimate test of everything you've learned in math. Can you write the equation of a line in any form, I don't care about that, with that slope, 0.75, that also goes through the 0.22? I had one person who could do it in period 1. But that's AB. You guys are BC. I've got to have at least 2. All right, yeah. You guys in your slope intercept form. Yep. Cool. Yep. Yep. All right. So the most common correct answer written in slope intercept form is y equals 0.75x plus 0.5. You actually could have left it in point slope form. I know there were a couple different ways that I saw it. So there is nothing stopping us from just doing point slope form, which would be y minus 2 equals 0.75 quantity x minus 2. Stuff we'll practice. I mean, you've got like a minute to learn it, but we'll practice it at a different time later on because this is something we'll be doing a whole ton of. But those both work. And as a matter of fact, I generally convert this to bring that 2 over the other side so we actually have a y equals equation. But those are all good answers there. But now kind of the grand finale of all of this, back to Desmos. I can put that line on my graph too. So let's see, 0.75x plus 0.5. Got it. And now when I move my slider, I have this set up to graph that line where the missing line was. You'll notice that other than a color change, we do have a nice smooth curve. The line hugs the curve nice and smoothly with the missing piece in it. And that's a tangent line. Okay. We're going to refer to that as a tangent line. That's the thing that we're going to spend the first several months of class learning about, and how we can get that number without just sort of guessing, hey, it sure feels like it's 0.75, things like that. So yeah. Yep. So main idea there really, you know, I popped back up to main idea really, the stuff that you have the tools to do now are find the slope of secant lines. You can put 2 points through a graph, find that slope. Put points through that graph, get them closer, find that slope. Calculus is you don't have 2 points, you only have 1 point. We have that one undefined thing in the table, and that's what we have to fill in. All right. You guys got a much better version than period 1 of that.